What's up, hackers? This is Tacit Sanctuary, and today we are going to build a library for Uiua from scratch. And on top of that, we are going to use some experimental features which resemble object-oriented programming. Wait a minute, what? Uiua is a stack-based array language. What does it have to do with OOP? After all, if you are watching this video, then you also must be a fan of exotic paradigms which are not so mainstream and boring. However, OOP does have some merits, at least if we forget about class inheritance, which is usually a terrible idea. And Viva recently got some interesting capabilities, which makes it quite simple to write OOP-like code. Now at this stage, Viva still has not released the final stable version. New features are introduced and old ones are removed or changed all the time. Exciting times in the life of programming language. And I am well aware that by the time I publish this video, some part of my code may already be deprecated. But living on the bleeding edge does also have some kind of romantic flair, don't you think? At least it is a unique thing in Viva that we can try the latest dev version in the online editor. So we are going to explore how experimental features work. In most programming languages, there are multiple data types that can represent numbers. There are integers and floats, signed and unsigned, and various types can occupy different amount of space in memory. This can give the developer a lot of power to optimize for performance, but it also adds a lot of complexity where we need to pay extra attention to things like type conversion and coercion rules or overflow. In contrast, the type system of Viva is very simple. There is only a single type for real numbers, and another one for complex, which I will ignore in this video. In any case, the numbers in Viva have a fixed size in memory, and while they probably work well for most use cases, we start seeing some loss of precision when we have to deal with really large or really tiny numbers. For example, we can see some digits misrepresented in the larger powers of 9. As a result, we cannot really do any precise math with large or tiny numbers, at least not at the moment. One example where this could be useful is problem 13 on projecteuler.net, titled Large Sum. Here the task is to figure out the first couple of digits after adding lots of 50-digit numbers. I can already see a problem just trying to parse a single number literal. Most of the digits are actually lost. So how to tackle this problem, working with large numbers? First, we have to find a suitable representation. The valuable digits in the number type may be limited, but luckily, this constraint does not exist for arrays. We can create arrays with fairly large element size. The obvious choice is to use a string to store the number, which preserves each digit as a character. But we cannot really use this for arithmetic operations. One idea that comes to mind is inspired by the bits function. This converts any number to a binary representation, an array of ones and zeros, starting from the smallest power of 2. For example, 20 is the sum of 4 and 16. We can use this idea to convert this string to an array of decimal digits, where each element will be a number from 0 to 9. The easy way is subtracting the 0 character from the string. Note that this will only work with natural numbers, so negatives are out of scope for this video. Then I will reverse it so the array starts with the last digit of the number. There are multiple reasons for this, most notably the size of the array can grow to the right when we have to add more digits. Also, by using character arithmetics, this function becomes easily invertible, so we can just convert the array back to string format just by applying the un modifier. Now that we have a way to represent a large number, let's do something useful with it. Implement the addition operation for two such numbers. Starting with a trivial example, I apply the digit function on both operands. Then I can actually do a normal addition to combine both arrays element-wise. Then revert it back to string format using the un modifier. This worked, but only because the two arrays were the same size. If this is not the case, then there is still an easy fix. Just filling 0 for the missing digits will align the different lengths correctly. This works because the leftmost digit is always the smallest decimal value. However, if I try this with a different pair of numbers, I can get strange results. I can inspect what is happening by showing the stack before and after the addition. From the debug data, it is clear that we have some double-digit numbers which are converted to the wrong characters. This gets quite obvious if we can remember how we did math in grade school, using pen and paper. Adding each pair of digits, starting from the last one, if the result is bigger than 9, then we need to carry the residue to the next digit. Basically, adding the two arrays like this is okay, but we need to normalize the result and carry all the residues all the way to the right. This may even result in additional digits. For example, when adding numbers of 3 digits, sometimes the result can have 4 digits. To normalize the array of digits, I need to shift the residues to the right. Keep in mind that the first element is the lowest decimal value. I can calculate the last digit of each element using modulus 10. And I can calculate the residual values dividing by 10 and then rounding down with the floor function. And I can do both operations at the same time with a fork. Rounding will be applied to the last value on the stack, which is the residue array. Now I use the join function to prepend the 0 to the residue values in order to shift them all to the right. Then I can add the two arrays with the 0 fill to match the shapes. This looks better, but there are still some problems. Even after this, the result may still contain two-digit values. So in that case, I have to keep iterating the same thing to carry the residue to the right until I have single digits everywhere. This can be done with the do function, which is similar to a while loop. I want to repeat as long as there is at least one value with double digits. So in the condition, I can write greater than 9, which will give a Boolean mask of all the digits. Then I use reduce maximum. So my loop will stop when all the values are single digit. Now my normalization function is completed, and I can finally convert my digits back to string. The only issue remaining is that the resulting string can sometimes start with a 0, or even with multiple zeros. This is meaningless for a number literal, so let's remove the leading zeros. First, I make a copy of this array with duplicate, and I make a mask for all digits greater than the 0 character. And here's another really cool array trick. Using a maximum scan, my mask will show true for all digits including and following the first non-zero character from left to right. And finish it off with the keep function to apply the mask on the digits that need to remain. I can put this into a separate trim function. And the addition is now also complete and deserves its own function. A little sidetrack here. If we are serious about using OOP in Uiua, first let's review how we can represent an object. What is an object anyway? Without delving into scientific definitions, I will just say that an object is a collection of values and potentially functions which work with those values. As long as these values have dedicated names, we call them fields, properties, or attributes. If these functions are encapsulated inside the object, we call them methods. Do we even need objects in Viva? Well, It depends. If we follow the strict Tacit principles, they may be of limited use, especially in very small programs. But to improve code reusability and to organize certain pieces of code in maintainable structures, this can be a useful concept to think about. In Viva, the simplest object is the array. We can put multiple values in an array as long as they have the same type. We can get away with such objects as long as we remember the meaning of the actual data which is included. Code comments can be useful there to document what each value represents. For example, this array could be an RGB color code. The next possibility is a bit poorly documented feature. We can add labels to each piece of data using the $sign. To make this work, the array must be boxed. This is basically just debug information or metadata attached to each value and has no effect on how the values behave. The labels are only displayed in the output, but not when we use the values, for example when printing to standard out or when converting to string. But unfortunately, we cannot use these labels to retrieve the values by name. The only way to break down such an object is through destructuring or picking the required value by index or by sequence. For example, using the first function. Also, we need to pay attention to unboxing the value. Potentially, a better option is using a map, where the field names are the keys in string format and we have the list of values. We can look up the fields with the get function. Now this might work pretty well, especially when all the values are the same type. It may get clumsy again when we need to deal with different types because each value must be boxed and unboxed before use. We may write something like this to create the map from a continued list of key value elements. We can also change the values easily with the insert function, which will just override the value at the specific key. Note, however, that it is not possible to put function references into an array without actually executing them. So creating objects where the fields and the methods are bundled together requires additional effort. For this, we can use modules in Viva, which are, simply put, namespaces with a limited scope. These modules can be saved in separate files to serve as libraries, which can then be imported to a different program from the file system or even directly from a Git repository. So they are actually very useful. A module is basically just a collection of names. We write a module in a block started and ended by 3 dashes. It can have one of two specialized functions, with the name new or call. These are supposed to represent a constructor. In other words, it can be invoked simply by writing the module name. For example, in the movie module, we can write a constructor which takes two values from the stack and bundles them in a boxed array to create a movie object. Then we can write additional functions that work on this data. Outside the module scope, I can reference the internal functions with a tilde sign. So now we know how to bundle fields and methods together. But this vanilla solution still suffers from the same problems that we observed before, having difficulty to refer to specific fields of the object. Unless we spell out the getter methods like in the previous example. Bear in mind, we are working with a language whose main design principle is to be tacit, meaning to avoid names. But at this point, there is an experimental feature called struct, which does try to solve this particular problem. Let's refactor the movie object using struct. I need to add the experimental keyword, or we might call it pragma. Using the struct keyword, I can use either a normal array or a boxed array to list the field names, just as normal text rather than strings. Based on this, my object will have a default constructor, and actual named fields which are visible in the output. And in addition, also the getter methods are created for me. I can reference the fields even without writing additional functions. Also, I can change the field values using the under function. I am going to use this pattern for my big number library. If you want to explore even more options, I also recommend to check the macros library by Marcoscat, which offers some utility to create struct and enum types of objects without relying on experimental features. Time to get back to my previous code and rewrite it using the module and struct concept. I need to add the experimental tag and enclose the code inside 3 dashes. The name of the module will be BigNut to indicate big natural numbers, and I will use the struct to encapsulate the content of the input parameter, which is a string. This internal field will be called n, but its name doesn't even matter much. I can already test that the constructor works and the string is contained inside the object. Now the only change needed is inside the add function. I must make it clear that the n value must be converted to digits. And finally, create a new object from the result string using the automatic constructor. Voila! The addition method works perfectly now. This is actually awesome. There are a few more things we can improve on this code. For one thing, I can add the type check to the incoming argument. To do this in the struct line, I just have to put a number after my field name. The type of any character array is 2. So in this case, I will get an error message if I try creating a BigNut object using a different type. However, only the type is validated, not the shape. So this is still not completely foolproof, but at least it is something. One more commonly used feature of OOP is that we do not necessarily want to expose all the internal mechanics of our library, like the dig, norm, or trim methods, only the user-facing parts. So we can hide some part of our code, making the names private using the binding tilde symbol. They are still accessible inside the module, but not from the external scope. After this, I get an error if I try to call the dig method from the outside. Now the next one might be a little controversial, especially in a public library. We can expose some of the names from the library by listing them after a tilde in the module header. The result of this is that now we are able to call this expose method even without the module prefix. It becomes part of the global namespace. And there lies the danger too, because it could clash with other names that we use or import inside the program. So I think this should only be used with extra caution. I would probably avoid doing this in a library that is intended to be used in larger programs. The BigNut library is already useful as it is, but we can still improve it, say by implementing multiplication. This should not be too difficult after what we have done so far. Now dig up your memories of grade school math class again, and remember how you did this on paper. Basically, multiply each digit of the first number by each digit of the second number. Shift the result to the proper decimal positions, and finally add all of them, taking care of the residual values too. How to do this in Uiua? The starting point will be again two big natural numbers. I use the dig function to convert them to the same format of decimal digit array. Then for now, I will work on this code outside of the module and will merge it later. Remember the steps. I have to pairwise multiply each digit of the two arrays. This is easy to do with the table modifier. We can observe that 3 times 7 is 21, which is the top left value in this matrix. So 1 will definitely be the last digit of the result. Also keep in mind that multiplication is a commutative operation. It means that the order of the two numbers doesn't matter. The result will be the same. So I could flip the arguments, or at this point I could transpose this table, it will not change the outcome. Also note that the length of the numbers doesn't matter at this point, and they do not need to be the same. The next step is to align the rows of this matrix in a way so that all numbers are shifted to the correct decimal position, similar to how we align them when we do this on paper. So the first line remains in place, the next one is shifted to the right by 1 position, the third line is shifted by 2 positions, and so on. So I need a range with as many elements as the number of lines. This is given by the length function, and to keep the matrix on the stack 2, I use the by modifier. And then I can create the range. Now I want to prepend as many zeros to each line as the corresponding value in my range. How to create a fixed number of zeros? This can be done with the keep function. If I just use a scalar argument, then I can create an array with a specific number of the same elements. So when I iterate through both arrays at the same time, I will insert a 0 after the counter with the dip modifier. Then keep the specific number of zeros to build up the array, and join it with the matching line of the other array. Now this almost works. The problem is that now each line will have a different length, so we cannot combine them back to a regular shaped array. Unless of course I use another field in front of the row iteration. This is what I was aiming for, and now I can collapse it to a single row with reduce plus. Great. Now this still does not look like a number, but we already have a way to normalize it to shift the residual digits to the right. Also, we can convert it back to string, trim the leading zeros, and create a new BigNet object just like in case of the addition. Also, we can verify it if the result is actually correct, because the example numbers are small enough for a regular multiplication too. There is one last thing that we can do to tidy up this code. Naturally, both the addition and the multiplication methods are structured very similarly. They convert the inputs, they do their own stuff, and finally they create a new object. We can extract all of the common code to a macro, and only keep the unique parts in each implementation. The multiplication code needs to be in parentheses because it contains more than one function call. The 2op macro can be private too. Ultimately, both of the functions are now working nicely. The usefulness and wider adoption of a programming language can really be boosted when developers can publicly share their libraries with each other. At the moment, there is no central package repository for Viva, such as we have crates for Rust or PyPy for Python. After all, Viva is still in development phase. However, there is an easy way for people to consume your code if you publish it in a Git repository, on GitHub, GitLab, or wherever you want. The main thing is that your shared code needs to be in a file called lib.ua. The import command, the tilde sign, can take an address of the repo as argument, and additionally the names you want to import from it, for example modules or functions. This actually also works in the online editor, so I have already posted this code to GitHub and I can import and use it from anywhere now. So doing addition and multiplication on big natural numbers takes only this much. I want to wrap it up by returning to the original problem in Project Euler, which was to add a bunch of really long numbers. I will solve it using my new library. Just for demonstration purpose, I will take only 5 of these numbers so we can see how to work with the library. First of all, I put the numbers in a multi-line string where each number is separated by new lines. I partition the string by the new line character, and each part is converted to a new BigNut instance. Now all I need is reduce this array with the add operation from my own library. This will pairwise combine two BigNut instances until we end up with a single value. Finally, I need only the first 10 characters of the result, so I have to extract the encapsulated string. I can do this with the default getter method, or even I can use the first function to reach the first and only value inside the object. And take 10 gives me the first 10 characters. This solution will work with any amount of numbers, 5 or 100 doesn't matter. Problem solved. Surely it is not the declared goal of Viva to promote the object-oriented programming style. But it is great that we have the opportunity to rely on such features if we want to structure our code in this manner. In some situations, particularly if we want to combine different types or shapes of data and potentially some behavior in a single object, we can take advantage of modules. And maybe even some of the experimental features such as struct will eventually make it to the final version of Viva. We have seen how easy it is to create and share a library over GitHub. This capability to consume code directly from a Git repo is truly amazing. My own library is by no means complete, but we managed to solve a particular math problem with its help, just importing it inside the online editor. There are a couple of other public libraries listed on the module tutorial page, so be sure to check them too. I hope you enjoyed this episode. If you don't want to miss future Viva content, then don't forget to subscribe to the channel. Your comments and suggestions are always welcome. Thank you for watching. See you in the next one.